Hi students, in today's session we are going to discuss about fusion reactors and we are coming to the end of our unit on nuclear transformations. We begin by discussing the advantages of fusion reaction over fission. The first advantage is that the energy released per kilogram of the reactants or of per kilogram of the starting materials in fusion is much more than that in fission. And the second advantage is that fusion reaction is relatively non-polluting when compared to fission. Now we are going to discuss a few fusion reactions, and we are going to see that by simply fusing two nuclei together, we are getting enormous amounts of energy. So in the first example, two deuterons or two deuterium nuclei are fusing together to form H13, that's tritium, plus H11, that's a proton, and with the release of 4 MeV of energy. Now, two neutrons can also combine in a different reaction route. That is, it can also combine to form He23 nucleus and a neutron with the release of 3.3 MeV of energy. In both cases, two neutrons are combining to release a very large amount of energy. Now, the major advantage of these fusion reactions is that deuteron or deuterium is present in seawater and it is very easy to extract these neutrons from or deuterium nuclei from seawater. So, deuterium can be very well used as a source in our fusion reaction because it is present in seawater which is highly abundant on earth and it's very easy to extract neutrons from seawater. But normally in a fusion reaction, we use a deuterium-tritium mixture as a fuel. We do not use deuteron or deuterium alone. We use a deuterium-tritium mixture as fuel because of two reasons. One is it has higher yield or it gives a greater amount of energy per reaction and it occurs at a lower temperature. So H13 plus H12 gives He24 plus N01, that is helium nucleus plus a neutron plus 17.6 MeV. That is a much larger amount of energy is released in this fusion reaction. But here the disadvantage is that seawater contains very little tritium, H13. So from where can we get tritium? It is produced by neutron bombardment of two isotopes of lithium. That is lithium 36 when bombarded with a neutron gives H13 tritium plus helium. And lithium 37, an isotope, when bombarded with neutron gives H13 again tritium plus helium plus a neutron. So that is the source of tritium. And tritium plus deuterium or neutron gives helium plus neutron plus 17.6 MeV of energy. So, deuterium-tritium mixture is used as fuel in the fusion reactors. Now, in the fusion reactors, the fuel will be in the form of plasma. It will be in the plasma state because for fusion reaction to take place, the temperature must be extremely high so that all matter will be present in a gaseous ionized state, that is the plasma state. Now you have to learn two new terms which will be used in these fusion reactors. That is, one is break even. Break even means the condition that occurs when the energy produced is equal to the energy input to the reacting plasma. That is, we say that the break even condition is achieved when the energy produced by the fusion reactor is equal to the energy given to the reacting plasma. And ignition. Ignition occurs when enough energy is produced for the reaction to be self-sustaining. That is, there is enough output energy produced for so that the reaction propagates or sustains on its own for the reaction to be self-sustaining, and that is called ignition. Now, three conditions are needed to be satisfied for a successful fusion reactor. One is an extremely high plasma temperature. That is, the plasma temperature must be so high that the ions have the speeds needed to come together and react in spite of their mutual repulsion. So the minimum temperature needed to ignite deuterium tritium plasma is 100 million Kelvin. So such a high temperature is required for the fusion reaction to take place. The next condition required for a successful fusion reaction is uh, high plasma density. That is, the plasma density is high to ensure a high collision frequency between the nuclei. And the third parameter required for a successful fusion reactor is suitable confinement quality parameter. Now, the reacting nuclei should remain together for a sufficiently long time, and this depends on the confinement quality parameter. Confinement quality parameter is the product of the number density of the reacting nuclei and tau, that is the confinement time. So, what is the density of the reacting nuclei remaining confined together for how long, for what time? So, the product of these two will give you the confinement quality parameter. So, for DT plasma at 100 million Kelvin, N tau must be greater than 10 raised to 20 seconds per meter cube for break even to occur. Next, what are the confinement methods? To confine plasma at high temperature, it's a very tedious task. So, two methods are used. One is magnetic confinement, where a magnetic field is used to confine the plasma. In the Russian designed tokamak, a magnetic field is in the form of a modified torus. The field lines are curved and the ions are moving in a helical path around these field lines. But here, these ions moving along the helical field lines can drift across and escape. To prevent this, a poloidal field whose field lines are in circles around the toroid axis is produced. Now, the poloidal field is produced by the current set up by the plasma itself by changing the by changing the field of the electromagnet at the center of the toroid. This current also heats up the plasma. So, I'll discuss once again. In tokamaks, the confinement of plasma is done by using a toroidal magnetic field. This is the toroidal magnetic field. And mm, here the field lines are curved and the ion moving in a helical path around its field lines can drift across this field and it can escape out. Now, to prevent the escape of the ions from the toroidal magnetic field, a poloidal magnetic field in this manner is applied. See, the poloidal magnetic field confines the ions in this region. So, the poloidal magnetic field is produced by the plasma itself and it's also used to heat up the plasma. So, this is one kind of confinement of the fuel or plasma for the fusion reaction. And the next method for the confinement of plasma is inertial confinement. In inertial confinement, the energetic beams to heat and compress the deuterium tritium pellets. We use energetic beams to heat and compress the deuterium tritium pellets by blasting them from all sides. അപ്പോൾ അതിശക്തമായ എനർജിയോട് കൂടിയ ബീമുകളെ ഉപയോഗിച്ചിട്ട് ഈ ഡ്യൂട്ടീരിയം ട്രീഷ്യം പെല്ലറ്റ്സിന്റെ മുകളിൽ വീഴാൻ അനുവദിക്കുകയാണ്. ഈ എനർജറ്റിക് ബീംസ് ഈ പെല്ലറ്റുകളെ ചൂടാക്കുകയും അവരെ കംപ്രസ് ചെയ്യുകയും ചെയ്യും. So laser beams have received most attention for inertial confinement. Electron and proton beams are also used. Now, what is taking place here? When the beam energy falls on the pellet, it is absorbed by the outer layer of the fuel pellet and it blows outward. The outer beam just explodes and blows outward. Now, to conserve momentum, an inward shock will take place and it will squeeze the rest of the pellet to say more than 100 times its original density, resulting in the heating of the fuel and starting of the fusion reaction. So this is how inertial confinement take place. Energetic beams are allowed to fall on the fuel pellets, and when the energy is absorbed by the outer layer of the pellet, it will just explode in the outward direction. To conserve momentum, there will be an inward shock. The outer layer is exploding outwards, and there will be an inward shock in a direction opposite to the direction of explosion, and it will squeeze the rest of the pellet to a very large number of times compared to its original density, which will heat the fuel and start the fusion reaction. So this is how inertial confinement takes place. So the fuel uh, in the fusion reactor is confined either by magnetic field using magnetic confinement method, where we first confine it using a toroidal field, and if the ions are escaping in, if we only use a toroidal field, then there is a possibility of the ions to escape. So we combine the toroidal field together with the colloidal field to prevent the ions from escaping from their region of confinement. So using magnetic field we can confine the plasma. The second method is inertial confinement, where we use high energy beams to fall on the fuel pellet and confine heat up the plasma and confine it there and allow the fusion reaction to take place. So these are the two methods of confinement. So I hope you have got an idea about what are the conditions required for a successful fusion reaction or a fusion reactor to operate, that is high temperature, then high collision frequency got by high plasma density, then suitable confinement quality parameter, and what are the different confinement methods. Now, I hope the session is clear to all of you. If you have any doubts, please do contact. Thank you.